You're hitting an API. Things are fine. Then this happens. HTTP 429. Too many requests. Your script stops, your job fails, and alerts start firing. And the API didn't break, your app did. You hit a rate limit. We'll cover both sides, what to do when you hit a limit, and how to build these yourself. Let's get into it. APIs usually throttle for 3 reasons. First one, fairness. One loud client shouldn't slow everyone else down, the noisy neighbor problem. Second is abuse. Screeping, credential stuffing, brute force, those kind of things. Limits are your first line of defense. Third is cost. Every request hits CPU, a database, maybe a paid downstream API. At scale, limits can keep the bill predictable. So 429 isn't the API being rude, it's the API protecting itself and the other clients trying to use it. Before you handle a rate limit, you should read what the server is trying to tell you. Most APIs put that information in response headers. Start with retry after. This one's a part of the HTTP standard. When the server sends a 429 or a 503, it can include retry after to tell you exactly how long to wait. 2 formats are common for this: a number of seconds or an HTTP date. If retry after is there, use it. You don't have to guess. The server knows better than you when it'll be ready. Then there's a second set you'll see commonly: X rate limit limit, X rate limit remaining, X rate limit reset. These aren't part of the official HTTP spec, they're just a popular convention. The names are self-explanatory, except reset. Some APIs send it as a Nginx timestamp, others as seconds until reset. Check before you parse. And different APIs can spell it differently. GitHub uses lowercase, X sticks an extra hyphen between rate and limit, and so on. Nothing's standardized. Read each API's docs. There's also an active IETF effort to formalize this without the X prefix. The current draft uses 2 fields, rate limit and rate limit policy. It's still a working group draft, not an RFC yet, but adoption is picking up. The point is that the server is telling you what's going on. Read the headers before you write retry logic. APIs use 4 common algorithms to enforce limits. Knowing which one you're hitting tells you how to handle it. First one is fixed window. The server counts requests in a fixed time bucket, say 100 in 1 minute. At the top of the next minute, the counter resets to 0. Simple to implement, but it has a bursting problem. You can fire 100 requests at 12:59 and another 100 at 12:01:00. 200 requests in 2 seconds, both technically legal. Second is sliding window. Same idea, but a moving window. Instead of resetting at fixed boundaries, it's always counting the last 60 seconds. More accurate, harder to game, but slightly more expensive to compute. Third is token bucket. Picture a bucket that holds, say, 10 tokens. Tokens drip in at a steady rate, 1 per second. Every request consumes 1 token. If the bucket's empty, you wait. If the bucket's full, you can burst, fire 10 requests instantly, and then you're rate limited until tokens refill. This is the most common pattern in modern API gateways and SDKs. It lets you burst for short stretches, but caps your average over time. Fourth is leaky bucket. Requests go into a queue at any weight, the server drains them out at a fixed rate. If the queue overflows, new requests get dropped. No bursting, but output is perfectly smooth. Here's how to tell them apart in the wild. If remaining ticks down and resets exactly on the minute, you're looking at fixed window. If it decays gradually with requests, sliding. If your bursts then stall, token bucket. If your requests get smoothed into a steady drip regardless of how fast you send them, leaky bucket. Okay, you know why limits exist, you can read the headers, and you can recognize the algorithm. So when you get 429, what do? First, respect retry after. Easiest fix, biggest payoff. If the server tells you when to come back then. The worst thing you can do is the naive loop. Retry immediately, no delay. You'll just keep getting 429, and you might get your IP or API key flagged for abuse. Then, exponential backoff with jitter. What if there's no retry after? Or you're handling other transient errors, 503, 502, connection resets. You back off exponentially. That means wait 1 second, then 2, then 4, then 8, capped at some maximum. Each retry doubles the delay. Exponential backoff has one nasty failure mode. Imagine 100 clients all fail at the moment. They all wait 1 second. They all retry at the instant they all fail again. Then they all wait 2 seconds. They're synchronized. That's a thundering herd, and it's how outages turn into longer outages. The fix is jitter. Add randomness to each delay so retries spread out instead of stampeding. The simplest version is called full jitter. Instead of waiting the exact backoff delay, you wait a random amount between 0 and that delay. AWS published a blog post on this years ago, exponential backoff and jitter, and it's been the standard playbook ever since. Here it is in code. Random, bounded, exponential. That's the whole pattern. Next tactic is queuing and concurrency caps. Backoff helps after you've already hit the limit. Concurrency caps stop you from hitting it in the first place. If you know an API allows 10 requests per second, don't fire 50 in parallel and hope for the best. Wrap your requests in a semaphore or a queue that caps how many can run at once. A simple async semaphore, 5 concurrent requests max, turns chaotic parallel traffic into something the API can handle. You go slightly slower on the happy path and dramatically faster on the bad path because you stop generating retries. And finally, caching to cut request volume. The fastest request is the one you don't make. If you're calling an endpoint that returns the same data for 10 minutes, exchange rates, configuration, a user profile, cache it. In memory, in Redis, behind a CDN, doesn't matter. Just don't ask twice. HTTP gives you tools for this. Cache control tells you how long a response is valid. ETAG and if non-match let you ask, did this change, and get back a 304 not modified, a tiny response with no body. Whether that 304 counts against your rate limit depends on the API. GitHub's a good example. An authenticated conditional request that returns 304 doesn't count against your limit at all. Check your API's docs. Even a tiny in-memory cache with a TTL can cut your request volume by an order of magnitude. Caching isn't glamorous. It's the highest leverage tactic on this list. So that's the client-side toolkit. Apply all 4 and you'll survive most rate limits without filing a support ticket. But these tactics have a ceiling.
What's that ceiling? 2 things usually. Volume means sending too many requests from a single IP address. Geography refers to making API requests from different countries. Either way, you need more IPs. This brings us to today's sponsor, a proxy provider useful when your workflows depend on geography, scale, or stable access across regions. They've got over 90 million residential IPs across 195 countries, and they don't resell from other providers. They provide 4 proxy types: residential, mobile, data center, and premium residential. Common use cases include web scraping at scale, SEO and SERP tracking with geo-specific results, and price monitoring across regions, cases where requests need to originate from different locations and stay consistent over time. Getting started is simple. Their intro plan starts at $5 and includes 5 gigabytes to test with real traffic. You can pick a country to target, that's included, save your configuration, and copy your credentials. You'll be up and running in less than a minute. By default, every request gets a fresh IP, or you can keep the same IP address for up to 120 minutes. HTTP, HTTPS, and SOCKS 5 all work. Response time is around a second. If anything breaks, support is available 24/7. Pay as you go, traffic doesn't expire. Just $1 per gigabyte for residential proxies. Links in the description for the $5 starter. Big thanks to DataImpulse for sponsoring. All right, let's get back to talking about rate limits.
We've covered the client side, what to do when you're hitting someone else's API. Now flip the perspective. What if you're the one building the API? How do you implement these limits? There are 3 places you can put your rate limiter: in your app, at the edge, or in a dedicated gateway. Let's go in order. Start with Redis. This is the workhorse pattern for rate limiting inside your app. Redis is fast, atomic, and it works across multiple app instances. The naive version uses INCR with an expire, and that's fixed window, and it's fine for a lot of use cases. But for a real token bucket, you want a small Lua script that runs autonomously inside Redis. The script reads the current token count, fills the bucket back up based on how much time has passed, takes one out, and writes it back, all in a single round trip, no race conditions. The handler evals the script. If it returns 1, the request goes through. If it returns 0, you return 429. But be careful. What do you key on? Per IP is easy, but punishes shared networks. Think offices, mobile carriers, anyone behind a NAT. Per API key is better, per user is better still. Most production systems layer multiple keys, IP level for abuse, user level for fairness. The second option is Nginx limit REQ. If you don't need to know who's calling, Nginx can do leaky bucket rate limiting in front of your service. A few lines of config, no code, no Redis. You define a zone, that's the shared memory where counters live, set a rate, and apply it to a location block. The burst parameter is the bucket size. How many requests can queue up before Nginx starts rejecting? Add no delay and bursts pass through immediately. Without it, Nginx spreads them out over time. One small gotcha to keep in mind, by default, Nginx rejects with 503 service unavailable, not 429. If you want the standard status code, set limit REQ status 429 explicitly. Most clients are looking for 429. This is the right choice for blanket protection at the edge. It's fast, battle-tested, runs in the same process as your reverse proxy. The trade-off is you can't easily limit per user or by what's in the request body. For that, push the limiter into your app or an API gateway. Your third option is API gateway. Once you're running serious traffic, you probably don't want to maintain rate limit logic yourself. Gateways like Kong, Tyke, AWS API Gateway, and Cloudflare all do this out of the box. You get plug-and-play limiters per route, per consumer, per key. You get analytics. The rate limit headers we talked about earlier are sent automatically. You give up some flexibility and you pay for the gateway, but for most teams past the prototype stage, it's worth it. Last piece is monitoring. If you're not measuring your rate limits, you're just guessing whether they work for you or against you. You should consider dashboarding these 3 signals. First, 429 rate. What percentage of requests are getting rate limited? Per route, per consumer. A healthy API has a small but non-zero 429 rate. That means the limits are doing their job and catching the right traffic. A 429 rate that's climbing means either an abusive client or a misconfigured limit, or both. Second, retry budget. Of your total traffic, how much is original versus retries? Google's SRE book uses a 10% retry budget. If retries are more than 10% of your total volume, your clients are stuck in back-off loops and you're wasting capacity on duplicate requests. And wait times. When a client gets 429, how long before they can come back? If those wait times are spiking, your limits might be too tight or your refill logic might be broken. All 3 together tell you whether your limits are doing their job or just creating noise. So, in short, rate limits are part of the API's contract. Design for them, don't react to them. Read the headers, back off with jitter, cap your concurrency, cache. And when you're building your own API, pick the algorithm that matches your traffic shape, key on the right thing, and watch the metrics. Links to everything I mentioned are in the description. If this was useful, the subscribe button does what you'd expect. Thanks, and see you in the next one.